So welcome back. The plan today is to finish all the discussion of the fast multipole method and how to parallelize it and a few other related topics, and then move on to structured grids, things like multi-grid and so forth. But before that, we'd like to make a couple announcements regarding homeworks. So the third homework is about to be posted, and Nick will tell you about that in just a moment. And I'm also planning to post a request that you make your project proposals. Start working on that. I'd like to, in principle, to see them before spring break so that I can give you some feedback on them over spring break. And Nick will talk about the third and final homework assignment.
So we're going to make homework 3 available today, and you can start out whenever you want. It will be due Tuesday after spring break, so that's Tuesday, April 3rd at midnight.
Better be April.
Sorry, I meant April 3rd. April 3rd.
Yes. Yes. So speaking of May 3rd, I'm not sure which day of the week that is, but I think it's RRR week. And the plan is to have a poster session for all of your project posters at the end of RRR week in some hallway with suitable drinks and coffee and so forth.
Thursday, May 3rd is actually the last day of class.
Okay, so we'll either do it Thursday or Friday. Okay, so are there any questions before we pick up where we left off last time? Yes? No, of last week of RRR week, so after instruction. So you get a few days to recover and then work on it. Yes. I think that's what RRR week is actually for, things like that. Yes. Yes. So last time I spent most of it on the mathematics of the Barnes-Hut and the fast multipole algorithm so that we knew how it could possibly compute these n-squared interactions and get a decent approximation in order n or log n time. And today I want to talk about parallelizing them. And there's been a lot of work on that since their inception. The most recent results I'll show you are from an IPDPS paper from 2010 where people did, there's yet new mathematics and a new algorithm and good speed-ups to show. But are there any questions about the overall structure of the algorithm before I start to parallelize it? So just to remind you, let's keep it in 2D just so it's easy to draw the pictures. I have a whole bunch of particles sitting in a two-dimensional space, and I'm going to build a quad tree. Divide space into 4 subsquares and then smaller subsquares and so forth. And for each of those, I'm going to build an expansion called an outer expansion that tells me if I'm far away from this particular little square, what's the potential due to all the particles inside? And the simplest example is simply all you need to know about all the particles inside a square is their total mass, Tm, and their center of mass, Cm. And if you're far enough away, that's all you need to know. But for the fast multipole method, we said, oh, that's just the first term of a Taylor expansion. We'll keep a few more terms, and so we can have more accuracy. So we traverse the tree once in order to build all those outer expansions. And that tells us that's good if we're far away from any group of particles. And then we traverse the tree one more time, going from top to bottom, and we compute what are called inner expansions. That's what we actually want, an expression for the potential inside each square due to everybody else who's far enough away. And so by the time we get to the bottom of the tree, for each little square, we have an expression that tells you what's the potential inside that little square due to everybody else who's basically not your nearest neighbor. Every square who's not your nearest neighbor. And that's almost everybody. So the final fourth step is, talk to your nearest neighbors and do the natural sort of n-squared interaction with them. And we did all the counting, and it turned into order n or order n log n. It depends a little bit on the shape of your tree and how uniform or non-uniform it is. So today I want to talk about how that stuff is parallelized. And I'm going to show you results that go back a ways. People have been working on it for a while, and as I said, results from 2010. And so this particular presentation was work of a PhD student here, where he tried to sort of pull together all the different schemes for parallelizing these things into an auto-tuner called P-body. So a parallel n-body code where he said, here are all the different ways, here's what the design space is for organizing this, and to try to give people opportunities for tuning. So what we have to do is the first step in any parallel code is you have to assign work to each processor. And the natural thing to do in this case is we're going to assign regions of space. I'll go into more detail. So each processor is going to be responsible for a subset of space, a subset of the squares in the quad tree or the cubes in the octree. And all those regions are going to have different shapes because we have to worry about getting load balance. So one processor may own a tiny bit of space if it has about as many particles in it as some other big piece of space. I'll show you pictures. There are different ways of doing that. Then each processor is going to be responsible. So what does that processor need to know in order to compute everything about it? Well, it needs to know all the expressions, all the quad tree for everything it owns and all its ancestors. So going up to the top of the tree, there's going to be redundant data kept because everybody needs to talk to the top of the tree over and over again as they traverse it. And so that's going to be a little bit of extra data. And then the most important observation that people made, many people made this observation, is that you also need a little bit of information from your neighbors, right? You need to have the information from the particles that are far away. So you need a little bit more of your quad tree, but as little as possible, right? Naturally, we want to communicate as little as necessary. And so the part of the tree that any particular part needs to own is called the locally essential tree. So it's a subset of the whole quad tree, and everybody's going to get just exactly what they need. And the question is, how do you decide what that is and give everybody their copies? OK, so let's go on to the load balancing question first. And the first thing that people tried was a pretty natural generalization of a quad tree. And what you do at every step is you pick the division. So at the first step, you have a vertical dividing line. You put it down the middle normally, but instead you put it either to the left or the right, so half of the particles are on one side and half are on the other. So let's suppose it divides evenly left and right. Then you go into each half, and now I'm going to pick a horizontal dividing line. And I pick it down here because half the particles are above the red line and half are below. And here it's different. Half are below, half are above, but I have to put the red line up there. And so now I have 4 sub-boxes bordered by the red and the blue. And I just keep going recursively. Next, I pick the light blue. So half are on the left, half are on the right, half left, half right. And then I pick the brown, half above, half below. And so it's still a quad tree from a data structure point of view, but it looks totally much more irregular. And I can deal with pretty much any distribution I want. And that worked pretty well in 2 dimensions, but this is just an empirical observation. It didn't work so well in 3 dimensions. You didn't have enough freedom of choice just by dividing into with straight lines or planes in 3D. So here's the other thing people tried. And this is called cost zones. And the idea is we're going to build the tree, and after we get the tree, we'll do the load balancing. We'll do the assignment. So here, imagine I have a complete tree, and it goes all the way down to the blue levels, these little blue squares with the blue borders. And in general, of course, it'll be sparser because it won't be regular. So what I'm going to do is order these leaves in some order from left to right. And I'm going to march across until here I have 4 processors until I get n over 4 particles. And I'll take the first n over 4 particles, and I'll assign them to the purple processor. And there they are. And then I'll start counting again until I get to the next n over 4 particles, and I'll assign them to the green processor. So the green processor owns those subsquares, and so on and so forth. So everybody's going to get an equal number of particles. And they're going to occupy some subset of the leaves of the quad tree, these little squares at the bottom. And so the question is, how do I choose the order to go from left to right in the leaves here? And we've seen this idea before. We had a different name for it. Let's see if we recognize it. So obviously, I want to have locality. So I'd like all of these different leaves to be close in physical space, not just leaves of the tree, because this guy's going to have to know a lot more information about his neighbors than he is somebody far away. So I'd like these to be close. So here is what they called it. They called it hashed quad trees. And what we're going to do is assign a unique identifier to each leaf, to each node in the tree. So the root will be 1. Its 4 children will be labeled 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And how do I get those numbers? Well, I just take the x coordinate, and I take the y coordinate, and I interleave their bits. So the x coordinate is the second bit, and the y coordinate, let's see. Do I get this right? The x coordinate is the second bit, and the y coordinate is the third bit. And then at the next level of the tree, so I add 1 more bit, and you can see, so all of these come first, then those, then those, then those. So we talked about this kind of ordering before when we were doing linear algebra. So what did we call this kind of ordering of a matrix? I mean, this looks like a matrix. So geometrically, it's a similar idea, even though there's no matrix here. We called it space-filling curves. And this happens to, or Morton ordering, that was the name we gave for it. And so for this particular ordering, where I do this corner, then that corner, then that corner, then that corner, and I do it recursively, that was called n, right? Because it's a shape of an n. And I can pick lots of, that's just because of the order in which I interleave the x and the y bits. I could have done it in different ways. And so in the old slides, I called this n Morton ordering. It's just one of many possible space-filling curves. So that's how I'm going to do it. So now that I've ordered all the blocks, how do I use that to assign particles to processors so that everybody gets as geometrically local a clump as possible? So here's the picture again, just to show you the numbering. And so now, let me just assume what I'm going to do is just my hash function is simply going to be the bottom h bits. So if I have 4 processors, I'm going to take the bottom 2 bits of this key that I've done. And I'm just going to start walking through all of these leaves, looking at their bottom 2 bits of each index, and keep on going until I have an equal number of particles. So I'll look at this one first, then that one, then that one. And at that point, I get to n over 4 particles. They all go to the purple processor. Then I go to the next, and then I start with the green one. And then I get him, then him, him, him. So all of these green ones go to the next. Then I come down here, and it's this order. This one, this one, this one. This one first, then this, this, this. OK, that's the order of the leaves. And finally, the pink processor gets the remainder, the remaining n over 4 particles. So as you can see, you're not guaranteed that everything is necessarily contiguous, but it does as good a job as possible, because that's what space-filling curves are about. They sort of try to draw a straight line through all of space so that things are close together. And so that's going to be the assignment that works particularly well in 3 dimensions of the leaves. And in general, I will not have if I have a non-uniform distribution of particles, some of these squares will be empty and they won't get assigned at all. And that's OK. OK, so the question is, how do I actually parallelize the construction of that object? The way I've described it is you've got to build the whole quad tree, and then you can walk through it and assign the work. That's not very parallel, right? I got to do this whole lot of work where there's a lot of communication because the particles are spread out who knows where, and then I get to figure it out. So we have to do something better. And the answer is random sampling. Each particle sends a small random sample of all of its particles to processor 1. Processor 1 hopes that that small random subset gives a good indication of where the dense clusters are and where the big pieces of empty space are. And it sequentially forms a quad tree just based on that small random sample, and then it tells everybody else what to do. So it's the master and everybody else is a slave, and it figures out the load balance, and with high probability, it does a good job. And if you send it more particles, it'll do a better job, it'll be more expensive, and life is trade-offs. So that's the, is there any questions about that first part? So why is it important to do this quickly? It's because these particles are moving. And every once in a while, we're going to have to repeat this process because they've moved around and we have to do load balancing again. So this doesn't have to be the fastest thing in the world, but it can't be sequential. OK. So the other thing that's important is that every processor is going to know the entire quad tree. So that's going to be some redundant memory. And why does every processor have to know where everybody owns stuff? It's because later, every processor is going to have to figure out which subset of this tree do I need, what's the locally essential part that I need from everybody else to collect so I can compute my local forces. And it sort of needs to have a pointer as to who owns what for that purpose. So that brings us to the next idea, which are these locally essential trees. And this idea goes back a while. And so, as I said, every processor needs a subset of the data. It doesn't need the whole quad tree. It just needs this, and the subset required to compute the forces on its particles. So for the parts of the tree that are very far away, it doesn't need the leaves from that part of the tree. It only needs roots that are vertices that are much closer to the root because you can summarize the stuff that's far away. So we're in the Milky Way. I only need a little bit of information from Andromeda. And so the processor that owns Andromeda will send me just a very little bit of information. That'll be my locally essential tree, probably just the center of mass and total mass for Andromeda. And so there are 2 ways people have implemented this in the past, depending on whether they were in a shared memory world or a distributed memory world. In the shared memory world, everybody just goes and grabs from shared memory the stuff that they need. And so that's why everybody needs to have this global data structure of who owns which processor is responsible for which part of the tree. The empirical observation from back then that didn't scale very well. that there was just too much data replication. But anyway, that's a natural thing to do. So the data I'm going to show you about is all big distributed memory parallel implementations. In that case, whoever owns the data has to figure out, what do I have to send to my neighbors? So that says it's sender-driven. So everybody looks at their parts of the subtree and says, oh, my neighbor to my left needs this part. I will package it up in a message and send it. And the other person will do a receive. And I do that for all my neighbors and send less and less information to my farther away neighbors. And so we need to have an algorithm to decide who owns what. OK. So the question is, how does each processor then decide which subset of its tree, of its quad tree, it needs to send to its neighbors? And there's sort of two different rules, because we have two different algorithms. There's Barnes-Hutt, and there's a fast multipole method. And Barnes-Hutt was trickier because we only used the mass in the center of mass, and it depended on knowing whether you could use this nice, simple approximation of mass and center of mass worked as follows. Let me just remind you. I can go back to the slides with the picture. So the question is, I have two processors, J and K, and N is a node on processor J. And what processor J has to decide is, do I have to send that information to my neighbor K? So how do you know? Well, what you do is you take that node, that's a node in the quad tree, and it has a side length. So it's a square, and the length of the side of a square is d. So the d of n is the size. And then the question is, how far away are all the particles in processor K? So let me pick the closest one. That's going to be the neediest particle. So r of n is the distance from the closest particle on my neighboring processor to this square. Now, what was the rule for Barnes-Hutt? The rule for Barnes-Hutt said that if d divided by r is small enough, then it's a good enough approximation. The mass and center of mass is a good approximation, and I should send it. But I don't want to send it if it's, for every little tiny one. I want to send the least information possible. So here's the rule. I'm going to send the information about this particular node in the tree if it's small enough to be accurate, so the size of the square divided by the distance is less than my user error tolerance. And I can't use my parent. My parent is not far enough away, but I am far enough away. And that's the rule. But also, I will also send everything from starting with the node that's small enough and far enough away and all its ancestors, because I will also need the parent and the grandparent and so forth. So that's the rule for Barnes-Hutt. So I just sort of traverse my subset of the tree, ask the simple question about each node, and send everybody, all the ancestors of that node on up. So that's the rule for Barnes-Hutt. And for fast multipole, it was a little bit simpler. And you may remember I drew these pictures with interaction zones and so forth. So you just sort of look at the interaction zones. Should I go back and show you that picture? Let me just do that for a moment to remind us all of what that picture was. See how long it takes to go back and forth here. All right. Is that big enough? All right, let's just do that. So this was the picture that we had for the fast multipole method. What information does this node need here? Once you're far enough away, you can use very big squares, all the Taylor expansions from these big guys. And then I need sort of my first cousins once removed. And so everybody except my nearest neighbors. And so this picture is easier to figure out. It's just sort of, how far away am I in the tree? And that determines the rule of what information has to be sent from n to everybody who's labeled all these different colors. OK. So that's the general scheme of how this works. Let me go back. OK. So any questions then before I start showing you some performance data where people have tried all these things and tried tuning all the different algorithms and seen what they got? So let me start with some really old data, which won a prize, and then move up to very recent data. So this was the Gordon Bell Prize paper from 1992, and it was on the biggest supercomputer of the day, which was an Intel Touchstone Delta, 512 processors, huge at the time. This is 8.8 million particles, and it's uniformly distributed. So one of the questions is, what if they're not uniformly distributed? This is the easy case, right? If it doesn't work in the uniformly distributed case, you're in trouble. And they were only trying to get, and this was Barnes-Hutt, and they were only trying to get between 2 digits to 3 digits of accuracy, so not very much. And so here is a total breakdown of the time. So let's look at this and ask ourselves, is this good enough? Did they do a good job? So the whole thing was 114 seconds. And here's the breakdown. So decomposing the domain, that's where everybody sent a subset of their particles to processor 1 to figure out what the quad tree, that was 7 seconds. Then everybody actually had to build the 3D, so octree, 8 seconds. Everybody had to traverse it up and down to build all those expansions I was telling you about. That was 33. So of those 33 seconds, some of the time was spent doing the matrix vector multiplies to compute the expansions or adding up the children's or whatever. And some of it was doing communication. So of that, 6 seconds was communication. And finally, the lion's share of the time is actually evaluating the forces at each particle, and that was 54 seconds. And the load imbalance, so this says the slowest processor finished 7 seconds after the fastest processor. So is this good? I mean, so if you measured this data and you'd implemented it, how would you decide whether you'd done a good job? What comparisons would you make, thinking as in, performance engineer, would you decide whether to declare victory or not? So what would you like to see all the time in which row? What would be obviously the best? All the time would be in which row? Force evaluation. If you spend 100% of your time evaluating forces, that means you'd be compute bound. You'd only be doing, the main job of the calculation, and all the communication would be negligible. And you couldn't ask for anything better than that. If everything were spent, all the time were spent here, just computing the forces, and if the load imbalance were 0 as well, that would be good. So how much? So if we were perfect, then how much faster could this go? I'd set that to 0. I'd spend no time doing that, no time doing that. This would go down by 7 seconds, right? So the slowest processor was 54, and the fastest one was 47, okay? So the best I could possibly imagine going would be 47 seconds, and instead, it took 114. That's not so bad, right? I'm within a factor of 3 of the best I could possibly have done. So that's the kind of analysis you sort of do when you ask, could I have done any better? Okay. So are there any questions? So you're going to be doing this, collecting a lot of this data for your own assignments and asking, did I do a good job or not? So you sort of build these models, on a piece of paper or in your head, and you ask, what parts of this are unavoidable, and I would love to spend all my time there, the force evaluation, and which parts are overhead. Okay. So that's old data. Let's go into some slightly more recent data, but not that recent yet. So move up to 1999. So this is the auto-tuned version of the code that graduate student David Blackston wrote here. And he was shooting for 4 digits of accuracy instead. And he was not scaling up to that many processors. He was using, in fact, this machine, which has direct memory access. So it was sort of shared memory. And so here are 2 examples just to show you the difference: a uniform distribution of particles and a very non-uniform distribution of particles, where they were, I think, sitting on the surface of a sphere in 3D. So very, very non-uniform. And here was the size of the tree, going from 1 processor to 4 processors. And here, again, going from 1 to 4. And the speed up on 4 processors was 4.4. And here, the speed up for the non-uniform case on 4 processors was 6.1. So when you see data like that, you should ask yourself, does that make sense? That's called superlinear speedup. So why should you not necessarily say, oh, the data's wrong? Why is this data possibly correct? Yes?
Where was it?
As you add more processors, you're able to split. You don't need to go and use a bunch of memory, so you don't have to hit the TLB, L2, L3.
Exactly. So we're not only increasing the number of processors, we're increasing the amount of memory, and that's why we can get superlinear speedup. I mean, we still are going to DRAM, but we have 4 times as much cache. Exactly. That's what's going on there. So we should not be surprised. We should be pleased to see that. It does also make the modeling question harder. You know, when do you declare success when you get superlinear speedup? You need to have a more detailed performance model of the memory traffic in order to do that. But the other important thing is, you know, the speedup versus the n squared code was even more significant. No surprise. You know, we're going from an n squared algorithm to an n log n algorithm. Okay. So let me go to some yet more recent data. This was presented at IPDPS in 2010. And this was comparing a whole bunch of different methods and doing auto-tuning across a bunch of different multi-core systems and GPUs. So the goal here was to compare these algorithms across a variety of platforms. And this was joint work between some folks here at LBL and some folks at Georgia Tech, including one of our former graduate students, Richard Vudock. So this was a cross-platform study, which of these different multi-core systems and some GPUs are the best for doing the fast multipole method. And so for that, they had to build an auto-tuner and try a whole bunch of different parameters. So they tried different data structures, because there are a lot of different data structures you could imagine using. SIMD, you tried that already on your homework assignment. But there's different sort of SIMD instructions to use for this particular problem. I'll tell you which ones. Different ways of doing multi-threading. Since we only want, you know, 5 or 6 digits of precision at the end, you don't have to use full precision everywhere. And so there are a bunch of instructions in the instruction set which let you do certain things to lower precision much more quickly. And if you use those carefully, you can get big speedups. I'll show you. And so what they got by all their tuning was 25x speedups on a 16-thread Intel Nehalem platform. Again, superlinear speedups. 9x on a Barcelona out of 8. And 37x on this hardware chip multi-threaded code of 128. And it was about as fast as the GPUs. So for this particular example, the algorithm was irregular enough that the GPU could not, you know, run at its full speed, and try as they might, it was about the same as the CPUs. And in fact, they only parallelized part of the code on the GPU, the force evaluation. All the tree traversals, all of that stuff was only done in the CPU because it was very hard to imagine how to do that on a GPU. So they also used a new version of this algorithm, which is much more general, and that you should know about. It's called the kernel-independent fast multipole method. And it works much more generally than for electrostatics or gravity or any of that. So if you remember how I derived the code, the algorithm, I said, OK, there's this mass in the center of mass, and then there's this Taylor expansion. I can take some more terms. And that was very specific to the 1 over r squared law. It turns out it works for anything, this idea about using these expansions. And all you have to give to this program is the formula, a subroutine for the formula, a subroutine that evaluates the answer when you have a single point potential. So all you need is a subroutine that knows how to compute 1 over r squared. Or if you're doing fluid mechanics, there's a similar kind of simple expression for Stokes flow. And there's other kinds of modified Laplace equations. All you need is a subroutine that computes this nice simple function, and you don't have to do any of the other mathematics that I told you about. It will all be done automatically by this algorithm. And so the idea, I should say, is that how do you approximate all the particles inside a region? Let's suppose it's a square. What you do is you surround the square by a circle, and you put a bunch of points equally spaced on the circle, and you say, let me replace all the particles inside the square by just a few points on the circle, and I'll pick the weights, the charges, whatever you want to call them, on those points in the circle to mimic all the particles inside. And that turns into a Fourier transform, because I'm evaluating a bunch of values on equally spaced points on a circle. And so most of the time is spent doing FFTs. And I won't do the mathematics, but it's a much more general code, but the same total, the same idea. You build a quad tree, you do an oct tree, you do a traversal from the bottom to the top to the bottom. All of it works the same, but the math is a little bit different, and it's much more general. So here's the different optimizations they tried. They tried this low-level SIMD stuff. Now, numerically, it turns out that you spend a lot of time computing 1 over the square root of x squared plus y squared plus z squared, right? That's if you're doing gravity or electrostatics, you got to compute 1 over r. And it turns out there's a special instruction on this particular platform that they use called an approximate reciprocal square root SIMD. And so what it will do is you can give it an array of 4 numbers, and for each one, it'll compute 1 over the square root of that number to half precision. And then you can run one step of Newton's method to make it almost good to single precision. And that gave them enormous speedups because that's where all the time went in computing these potentials. So that's, if you have an inverse square law or something like it, you'll want to use it. They also tried lots of different data structures because there's structure of arrays or arrays of structures. You can sort of transpose all the data structures inside, and that affects how they get vectorized differently. So this was another detail inside the algorithm. There's still things that smell like matrix vector multiplies, but they did them differently by using stencils. And then, of course, you can tune the heck out of the FFT, and they used FFTW for that purpose. And they used OpenMP to parallelize it. And finally, remember, when we keep on refining the quad tree or the oct tree, and we stop when there's a certain number of particles in each leaf, and that number of particles they called Q, and that was another tuning parameter. When do you stop? Because at that point, we're going to do Q direct interactions. And so that depends on the architecture. So here's the data. So let's just talk about Nehalem. So this was a single core optimization, no parallelism yet, running in double precision. And this is for a very non-uniform distribution. So all the particles are uniformly distributed over an ellipsoid in 3 dimensions. So they're sitting on this 2-dimensional surface. And these are the different phases of the algorithm. 0% is the code before. That's sort of 0% means you're running at exactly the speed of the unoptimized code. And up means this is what the speed up was. 100% is 2 times faster. 200% is 3 times faster. And going down is, whoops, it's slowing down. And so there's a lot of different tree traversals because the algorithm is a little bit more complicated. And they've broken it down into these pieces. And SIMDization is the red speed up. Replacing the reciprocal square root with the new SIMD approximate reciprocal square root and doing a little Newton gives you this enormous speed up of yellow. Changing the data structures and transposing them was the green speed up. And then getting rid of the matrices and doing the FFTs, getting rid of the matrices is purple, and FFTW helped in that particular region. So altogether, these different regions sped up quite a bit. And this was Nehalem, and their software, of course, works on Barcelona and all the other kind of auto-tuning, all the other target platforms. Here's just another snapshot of what happened when they tuned for the number of particles at the bottom of the tree in each leaf. And so there's both the reference serial code. So the vertical axis is second, so down is good. The horizontal axis is Q, how many particles per box. And there's 3 codes they tried tuning, the untuned, unoptimized code, then the optimized serial code, and finally the optimized parallel code. And so for a while, it goes down, and then it goes up again. So there's a sweet spot of how many particles you want to have per box. And, well, 168 down to 10.4. So that's how many particles were left at the bottom, and that was found by auto-tuning. And finally, here's sort of the global comparison of over all the different platforms. So Nehalem, Intel Nehalem, AMD Barcelona, Sun Victoria Falls, and 1 GPU and 2 GPUs. And here's a uniform distribution of particles. That's sort of the easiest case. And here's everybody sitting on an ellipsoid distribution of particles. And 1, so this is a log scale. 1 means you're running just as fast as a single Nehalem. And up means you're 10 times faster or 100 times faster. And down means you're whatever, this should be 0.1, 10 times slower, 100 times slower. And so 1 Nehalem is sitting there. By the time you've optimized the single processor code, you're going 8 times faster. By the time you've parallelized it to do OpenMP, you're up here at 20 times faster. And then if you just throw out all of the tree construction and just look at the force part, which is where most of the time you hope gets spent, it's 54 times faster. So the inner loop, the hard part, went 54 times faster. And there were similar good speedups on Barcelona. The speedups are best for uniform. They're not quite as good when it's a non-uniform distribution. No surprise, it makes the load balancing a little bit harder. Sun Victoria Falls, doesn't, even with 128 threads, it still can only beat the single processor Nehalem by a factor of 3. And then here are the GPUs. And the GPUs are colored all green because they didn't even try to do all the tree construction and so forth on the GPU. That was all done in the CPU, so they're only computing the forces once you've built everything. And they got good speed ups there, but it isn't even counting all the other time. And going from 1 GPU to 2 GPUs, the speed up went from 30 to 60, so it's pretty close to a factor of 2. Okay. So that's sort of the state of the art as of a couple of years ago. And needless to say, it's an important algorithm, so people keep working on it. So let me sort of, are there any questions about that performance data? So this is sort of now the last topic I want to talk about in n-body, which is how do we know if we've done as best as we can from the point of view of communicating as little as possible, right? Because that's one of our general goals. And the whole point of that locally essential tree that I told you about was that each processor would get a copy of just exactly what it needed, no more, and then compute locally with it. So people have been trying to do this for a while. The question is, are there lower bounds that we can provably attain? And let me just say, for all the methods I've talked about so far in this lecture, the hierarchical method, so fast multipole and Barnes-Hut, it's a totally open problem. Because they're complicated algorithms. Your answer is approximate, so the lower bound is probably going to depend on how much accuracy you want. And the lower bound may also depend on the particle distribution, and so nobody has a good answer for that. On the other hand, for the direct methods, and all of these problems actually run the direct methods eventually at the bottom of the tree, there is a lower bound. And so let me just tell you what it is. So suppose I have p processors, and I'm doing n particles, so there's a total of n squared interactions. And let's suppose that each processor has a memory of size m. So the question is, what's the minimum amount of communication that each processor has to be able to do? So let's assume it's load balanced. So every processor is going to do n squared over p work. Then a lower bound on how much communication any processor has to do, so big omega is lower bounded by the number of particle interactions it does divided by its local memory size. That is a guaranteed lower bound on if you're running the direct method. So every particle has to eventually meet with every other particle and compute an interaction, so they're n squared altogether. That's the lower bound on the words moved. And the number of messages, if you send messages that are as big as possible, it's lower by a factor of m. So that's divided by m, that's divided by m squared. And that's true for, well, many different values of m, right? I didn't tell you what m is yet. So what's the least I can get away with? If there's one copy of every particle on every processor, and there's n particles, then n over p is the smallest memory. But if I keep making m bigger and bigger, then this lower bound decreases. And the question is this attainable? So are there algorithms that actually do this? Okay. And let me say this theorem is much more general. I don't actually have to do all n squared interactions, because in a lot of cases they're cutoff distances. I'm only going to interact with particles that are within a certain distance. In that case, the number of interactions isn't n squared anymore. It's just some number that depends on the algorithm. In that case, the theorem is still true. All I'm going to do is replace n squared by the actual number of interactions that the algorithm performs. So this is true for a very wide number of algorithms. And the question is it attainable? So let's look at the traditional algorithm and just ask ourselves, the one that we learned about quite a while ago, and let's just see how close we get. So I'm going to have n particles here, and each dot is a particle, p processors, and I'll assume I only have enough data for basically one copy of each particle. And so what was the algorithm that we had before? Simply everybody takes a copy of their particles and sends it to their neighbor. And then this particle computes all the interactions. And then this processor then forwards the data from there to there, from there to there. So every copy of the particles just goes all around in a circle, visits every processor once, and every pair of interactions is computed. That was the algorithm we had before. So there's sort of this ring of communication. Everybody sends data to their neighbors. So what does that cost? Well, it's perfectly load balanced. Everybody's doing n squared over p work. And how much communication is there? Well, every particle has to go from here to here to here to here. Every particle moves, and so there's an order n words moved, because every particle has to visit every processor, and so the bandwidth cost is order n. Let's compare that to our lower bound. The lower bound was the number of interactions done by that processor divided by its memory size, and it matches. So as long as we only have that much memory, we're not going to do better. How about the number of messages? Well, everybody has to send from there to there to there to there. They're p messages. And so because every processor has to send its information p times, and so p messages, and what's the lower bound? If I compute it, it's again order p. So this is also optimal. And so the question is, can we do better? than optimal. And so let me speak by analogy here. Remember when we talked about matrix multiply? And we said if you only have enough memory for one copy of your matrix, there was a lower bound, it was attained. And then I said, oh, what if we have enough memory for more copies? We actually had a different algorithm that was asymptotically faster. And we do here too. And just as like we called the matrix multiply algorithm 2.5 dimensional because of the way the processor layout went, here we're going to call it 1.5 dimensional, again because of the way the processors are laid out. So here's how it works. So suppose I have enough memory not for just one copy of all the particles, but for C copies. So C, depends on how much memory you have. So I'm going to start by assuming that I spread out all my particles over not all the processors, but just P over C of them. Okay, so if I have enough if I have enough memory for 4 copies, this is a quarter of the processors, and let's assume all the data starts there. Then what I'm going to do is take the rest of the processors and just make copies of all the data. So all these particles, I'm just going to copy down and make 4 copies. So let me just draw the picture here. So all these particles are going to be the same. So here I have P over 4, C equals 4 here. Processors, and here I have this many particles, and each of these blue boxes is going to have a copy of the particles in the top, right? So I'm just replicating. So now, and that's going to cost me some communication. I'll count it in a second. So now what's the algorithm? So the algorithm says each processor in each row is going to take its data and send it, well, to itself, to its first neighbor, to its second neighbor, to its third neighbor, and so forth, in a little staggered pattern. I'm just showing you what happens here with the first column. This guy is going to do the same thing. This is going to stay where it is. This guy's data is going to move over to 1. This guy's data is going to move over 2. This guy's data is going to move over 3. So everybody does a sideways shift. So now all the data is set up, and I'm ready to start running the algorithm. I haven't done anything yet, I haven't done any arithmetic yet. And so the main loop of the algorithm says that I'm just going to keep on copying this data over. So now I compute all the interactions here in this diagonal. Then I shift it over by P over C, compute all these interactions, shift it over again, shift it over again. And how many times do I have to do that? P over C squared times. Okay. And I'm not going to do all the algebra, but every particle eventually visits every other particle in a different processor. And what each processor now has a subset of all the interactions. So this guy has not computed all the interactions of its particles with every other part. It's only done a quarter of the work. And so the final step is I take all of the contributions from each column and I do a reduction. I sum them all up to the first row. And now everybody has the sum of all the. So each row has done a quarter of the work, has done a quarter of the interactions, and I sum them all, and finally the first row has the right answer. Okay. So I won't try to write down all the algebra. But let's ask ourselves how much this costs. So let me just leave the algorithm there, and I'm just going to write down all the costs. So the first step was make a bunch of copies. Take this guy and broadcast him everywhere. So that cost me log C messages to do a broadcast. And he's sending everything he owns, so it's n times C over P. That's how big this stuff is. Now the main algorithm, as I said, takes P over C squared steps. As I go from there to there to there and so forth. Each step is one message, so latency of 1. And I'm sending everything I own, which is NC over P. There are this many steps, so I take the number of steps, multiply it by this, and here I get the latency cost is P over C squared. Remember, it used to be P. Now it's P over C squared. And now the bandwidth has gone from N, what it used to be, now it's N over C. And that equals the lower bounds, the new lower bounds. So this is actually a new optimal algorithm that works as I keep increasing the amount of memory. Now, how much can I increase the amount of memory? So how far, when does this, when does the game stop? How much can I keep going? Well, I claim it stops when you hit the square root of P. And this processor grid becomes square. Square root of P by square root of P. That's sort of the limit. So let me just draw a picture of that. So this is sort of the limiting case. So every processor broadcasts down, broadcasts sideways, and then there's just one step in the loop. So remember the main loop here for P, I loop from 1 to P over C squared, when p over c squared equals 1, that's the limit of this algorithm. And that's what it looks like. And in that case, the main part of the algorithm has one step, and the cost has dropped to n over the square root of p. So the bandwidth cost has gone from n to n over the square root of p, and that is the global lower bound that's possible for direct n-body. So it turns out that to prove this, so I made this claim here about n-body, and I made a similar claim about an optimal matrix multiply algorithm. They're both special cases of the same general result. There's a sort of a general theory that gives you lower bounds for linear algebra, for n-body, and for a very large number of other problems. And we'll talk about that general result later in the semester. But these are two examples where we've got new algorithms that are asymptotically faster. So any questions? That's the last thing I wanted to say about n-body before I move on to structured grids. Okay. So we are moving our way through the 7 dwarfs. And so this is where we are. So far, we talked about dense matrices and sparse matrices and n-body. And now we've moved up to structured grids. And so there's a lot of different algorithms here. But having done sparse matrices already, you'll see by analogy, there's a lot of sort of common ideas. So here are the topics I want to talk about. And I want to have a driving application to sort of motivate these different algorithms for parallelizing structured grids. And image recognition, image segmentation is one that's a Parlab application. But I'm going to pick one from differential equations just because it sort of covers all the different algorithms, and it's easy to sort of tie it all together. But these are used in lots of different things. So I'm just going to very briefly remind you about Poisson's equation. And that'll be our driving application. And all the different methods for the Poisson equation. I had a table of which ones. And then I'll pick out these 4. I'm only going to really talk about 3 of them: Jacobi, SOR, and multigrid, because those illustrate all of the interesting parallelization locality issues for working on structured grids. Now, if you want to solve Poisson's equation, FFTs are good too. That's another lecture. So just to remind you about PDEs, there's 3 different kinds. They're all solved using structured meshes, structured grids. There's wave equations. There's steady state stuff like gravity and electrostatics. And then there's parabolic equations where it's like heat, where things do change from time step to time step. But from a parallelization point of view, they have 3 really different properties. For things that are waves, you only depend on your nearest neighbors, right? Because things move at the speed of sound or the speed of light. And so your mesh only ever has to talk to your nearest neighbors to do an update from one time step to the next. And these methods are pretty straightforward to parallelize. But there's still some optimizations that are interesting. The hardest case is, well, elliptic problems, so gravity and electrostatics, like I talked about before, because everything, the solution at every point depends on all the data everywhere else. And here we have to be much more clever. And just as the fast multipole method was kind of motivated by this, the multigrid method that I'll tell you about here is motivated by a similar question. How do I minimize the amount of communication that goes all the way across the grid? And then parabolic has to solve an elliptic problem at every time step. So this one is at least as hard as that one. But just to keep it easy, I'm just going to focus on the canonical example that we've used before, which is the Poisson equation. So the sum of all these second derivatives is some function. So, but let me just quickly say what, establish the notation by talking about the wave equation, because that's the easiest one. So what I'm going to do at every time step, basically, is take the values on a grid and average them to get the next one. So here's my iteration space. So the vertical axis is time. So time I equals 0, time I equals 1, 2, 3, and so forth. And so I'm going to have an index here where the time is I times some delta. And then at each time step, I'm going to have the value of the solution at a bunch of grid points. And J is going to be my index for the grid points. So here are all the values of my wave at time I equals 0. So that's the second subscript. And the first subscript, j, is going to run from 0 to 5 as I move along my array. And so the algorithm couldn't be simpler. I'm going to loop from the 0th time step. I'm going to loop from the jth point, j equals 0, over to here. And I'm going to compute the solution at time step I plus 1. It's going to be a function of the solution at time step I. And it's just going to be a linear combination of the 3 nearest neighbors. So here's the picture. Suppose that I've computed all the solution at time step I equals 2. I want to compute the solution at time step I equals 3. To get that guy, I just take a weighted sum of these 3 neighbors. So they're the 3 arrows indicating the dependencies. And I'm going to do that at every one of these mesh points. So there's the nice simple loop. So that is the way you might write the code as simply as possible. And to draw the analogy with what we did before, because it's going to be the same optimization techniques for structured grids as for sparse matrices, here's the inner loop of the algorithm again. The solution at time step I plus 1 depends on the solution at time step I, and I just take linear combinations of my nearest neighbors. So j has nearest neighbors j minus 1, j, and j plus 1. And since this is a linear combination, there's really a matrix vector multiply hidden in here. And so if I take the vector of all the u's at time step I, so there's all the solutions at time step I, to get to time step I plus 1, all I do is I multiply that vector by this tridiagonal matrix. And the tridiagonal matrix has some z's, some 1 minus 2 z's on the diagonal, and z's on the superdiagonal. So I just copy these numbers here. And then I notice that this is equal to, that should be L equals my favorite matrix, which is just the Poisson equation. So I'm taking -1 times my neighbors and adding 2 to myself, and that's the Laplace operator. So this is a typical picture. And so here's the matrix version of it. And since I'm doing structured grids, I'm going to take advantage of the fact that all these numbers are 2. I'm not going to store them actually. And all these numbers are -1. And all I need to know is that I'm repeating this stencil at every point in my mesh. 2 times that value, minus that neighbor, minus that neighbor. So that's the one-dimensional version. And then here's the two-dimensional version. And so we talked about this one before. In 2D, again, it's a matrix vector multiply, but it's easier to say at each mesh point, I'll take 4 times that value and -1 times all the neighbors. And so the question is, this is what I keep doing over and over again. And so what are the right ways to optimize that? Because I don't want to store that matrix, and I want to minimize communication. So these are all for solving Poisson's equation. And so in an early lecture, I put up a table of all the algorithms for solving Poisson's equation. And we've come back and talked about these at various times. And these are algorithms that range from dense Gaussian elimination, which pay no attention to this beautiful structure of the matrix at all, down to multigrid, which is super fast, linear time, optimal. We haven't gotten there yet. And all of these are sorted by how long they take. So n cubed for dense Gaussian elimination, down to multigrid, order n. This is a serial time. This is how long it would take on a perfect parallel machine where you have as many processors as you want and communication is free. And so this is just sort of tells you how intrinsically parallel they are. And what this lecture is about is how to optimize these particular algorithms. So Jacobi, conjugate gradients, red-black SOR, and then the winner of all is multigrid. So all of these are going to use the same optimization techniques. And so, and multigrid is built out of the guys above it, right? So I got to talk about Jacobi and SOR to tell you how to build multigrid. Okay, but I'm going to start with the easy stuff. I'm going to start with Jacobi and explain how to parallelize that and minimize communication, and then say more about these, and then probably next time I'll do multigrid. Okay, so let me just write down on one slide the math of Jacobi, and then talk about how it's parallelized. So here's what I need to do. This is just copied from a previous slide. So here, so what I want to do, I'm going to do it in 2 dimensions. So now u sub ij is the solution of the equation at mesh point I comma j. So it's 2D Poisson. And so what's the equation? It says that the value at this mesh point is equal to a particular weighted sum of all its neighbors. There's its neighbor to the left, to the right, below, and above. So these are its 4 nearest neighbors plus the right-hand side divided by 4. So all I've done is taken my equation, tx equals b, and reorganized it, tu equals b. And here I've written it u equals combination of its neighbors. So what does Jacobi say? It says, let's suppose that I have my mth approximation. I've taken m steps of my algorithm, so I'm going to add an index, and I have my mth approximation to everybody. How do I get the m plus first approximation? I'll just make sure that this equation is satisfied. So I'll take the mth approximation of all these guys, plug it in to get the m plus first. So every step of Jacobi simply says, let me perfectly satisfy one of the equations. So everybody's going to change, and this is the simplest thing you could do. It's just a weighted average of all the neighbors. And now, of course, when I change all these values, not every equation is suddenly magically satisfied in one step. It converges, at some rate. And so the question is, how fast does it converge, and how do we implement it quickly? So it turns out that for Poisson's equation, it takes quite a few steps to converge. It takes about n squared steps to knock down the error, because information moves very slowly. But nonetheless, it's a building block that we need to use. So why does it converge so slowly? Let me just sort of draw a picture to explain it. So let's suppose that my right-hand side, my b vector, is only one in the middle. So think of gravity where there's just the sun and nothing else. So, and here is the solution, 1 over r squared. And so so this is the function I want to compute. I start with a value 1 in the middle, 0 everywhere else, and this is what I want to converge the solution to. This is what x is supposed to look like. Now remember, what is Jacobi going to do? It's going to start with a solution which is 0 everywhere, and repeatedly average with the nearest neighbors. So let's ask ourselves, what happens if I start with this solution? Here it is. Here's the right-hand side. It's just 0 in the middle. There's the sun. And all I get to do is average with the nearest neighbors. So what happens if I just average with my nearest neighbors once? Where can I have a non-zero answer? Just the immediate neighbors of the sun. Now, I do another step. Where can I have a non-zero answer? Second nearest neighbors, right? And so after I do whatever this is, 4 nearest neighbors, I can't get non-zeros anywhere out there. Remember, I'm trying to get to this solution. It's non-zero everywhere. And so if I take 4, what's the best I could possibly hope for after 4 steps? The perfect answer there, and then it's got to be 0 farther away, right? Because I'm averaging zeros. If I take 4 steps and I'm more than 4 steps away, I can't possibly do better than that. So the error, no matter what I do, if all I ever do is average with my nearest neighbor, is going to be the height of that cliff. So this is just the true solution, and then zero it out when you're more than 4 steps away. So the height of that cliff is going to be a lower bound on any algorithm. And it's not very good. That's why it takes so long to converge. Still, it's a building block, and we have to parallelize it. But we have to come back and fix this problem that information moves one cell, one grid point at a time. That's just too slow. So how do we parallelize Jacobi? So here is the algorithm written down yet one more time. I'm going to take all the values at time step m, do a matrix vector multiply, and add in the right-hand side, and to get all the iterations at step m plus 1. So here's my 2-dimensional mesh. And what I need to do is assign all the points to processors. And we've seen this picture before. Let's suppose I assign them all to these rectangles. So there's a blue rectangle. He's responsible for computing all these mesh points, a red one, a purple one, and a green one. And so each processor is going to want to compute the weighted sum of the neighbors for every point inside. And there's no communication. It's perfectly parallel. And there's no communication unless you're on the border. So this guy, all these 3 are locally stored in this upper processor. But for that, there's communication. And we've seen this before. This is the graph partitioning problem on a nice regular mesh. And we know that the surface to volume ratio, how big is that surface, is going to determine how much we communicate. And we've seen that issue come up before in my lectures on sparse matrix vector multiply. But this is different. This is easier, or we have more opportunities to parallelize because I don't have to store the matrix entries, right? The matrix entries are known. There's 4s and -1s. There's no memory. There's no memory traffic. There's no communication for any of those. So let's just see what happens to our old optimizations for sparse matrix vector multiply and how they apply here. And let me draw the picture first in the case of a 1-dimensional stencil. So just to keep it easy, instead of 2D, I'll draw that eventually. So I just want to compute my average with my nearest neighbors. So here's the vector x I want to start with. Here's my first iteration. I'll call that a times x. There's my second iteration, all these mesh points, a squared. And there's the third iteration. And this is going to be, and so remember, I drew this picture before. Since I'm only dependent on my nearest neighbors, this iteration depends on the 3 nearest neighbors in the previous iteration. And so just to recall, what was our sequential algorithm for this? In step 1, what am I going to do? I'm going to read in all these entries of x. And because of that dependency, I now, with no more memory traffic, have all the information I need to compute everybody inside that blue trapezoid, right? Because everybody just depends on the 3 nearest neighbors below. And if you follow the dependencies from every point, this is enough to compute everybody inside that blue parallelogram. So we call that, I showed you this picture before, but why is this one even better? So when I did this one before, I also had to read in the matrix, right? I don't have to read in the matrix anymore because I know it's -1s and so forth. But there's something even better, right? What do I have to write out at the end when I'm done? So when I did this thing before, I actually needed to know what a times x and a squared times x and a cubed times x were. But now, all I care about is the last step. I don't care about all the intermediate steps. I just want to converge, and the last guy is the best answer. So that means, how's the algorithm going to work? I'm just going to have 2 rows. I'm going to have x, and I'll have another array, a times x, and then I do ping pong. Then I update this guy, and I copy him into the original data, because I don't need him anymore. And so I don't need to store everything inside this blue trapezoid. I only need 2 rows. And when I'm done, I only read out the last row. And so the memory traffic doesn't depend on how many steps I take. It's just a constant. So this is a whole lot better than it was before. So that means that I read in all these rows of x. I compute the blue parallelogram. I write out everybody at the top. But I have to keep the border, because the next step is going to need the data on the border. Then I read in all of these values of x. And I've kept these guys around. That's enough information to finish up everybody in the red parallelogram. And when I'm done, I just write out the top row of the red parallelogram. But I keep everybody along this border. Then I do the same thing for the green. Read in the bottom row, compute everybody inside the green, only write out the top row, keep the border, and then finish the yellow. So now the communication doesn't depend on how many steps I take at all. It's just order n. Yes? Question? The microphone?
So for the first element of a dot x, we just have 2 elements down. So we have
right. So for this guy, the dependency, there's nobody over here.
Yeah.
And that's the first. That's the top corner of the stencil, if you like. So he only depends on those 2, and that's okay. Yeah. There's always boundary conditions, and here the boundaries. I'm just saying there's 0, so it's easy. Yes.
That's just a quick thing. Step 2 is parallelogram is bigger than step 3 is that.
So that's just bad art. So. So you should think of each of these as having the same area, and you should use your whole local memory in order to do this optimization as well as possible. Okay, so that's the sequential optimization that minimizes the traffic between main memory and cache to do this update. And so what about the parallel optimization? And again, it's going to be analogous to the one that we did before. I'm going to have, let's say, 4 processors. Each processor is going to get assigned to compute the first quarter of those entries, the next quarter. So processor 1 is going to be responsible for computing everybody in that blue parallelogram. But he needs some data from his neighbor. And so the trick we did before is that processor 1 owns everybody at the bottom. He owns x1 through x8. But he needs to take 3 steps, 3 more values from processor 2. So processor 2 will package these up in one message, send them to processor 1, which then has enough information to compute everything inside the blue trapezoid. And then processor 2 will similarly get one message from processor 1 with those 3 numbers, one message from processor 3, and then compute everything inside that, and only has to keep the stuff at the top. And that's what processor 3 will do and processor 4. And so all of these little triangles here will, of course, be computed redundantly. So I've sort of color-coded what every processor is responsible for, and everything inside this purple triangle is going to be done redundantly by processor 1 and processor 2, and similarly for that triangle. So the price we pay to minimize the number of messages is a little bit of redundant work at the corners. But if this is long enough, it's worth doing. So I've drawn this picture in 1 dimension because it's easiest to do, but it obviously works in 2 dimensions. And so here's what the pattern would look like now if I have a 2-dimensional mesh. So each of these little squares is one of the solution points in my grid. So there's the x's. There, the next layer up that's parallel to it, that's ax. This layer is a squared x. That layer is a cubed x. And so and this is one square, and these green lines are the borders between processors. And so what does this processor need to get from its neighbors to compute everything here? It needs to get this data from this neighboring processor, that data from that neighboring processor. So it's going to grab all of these 3 rows, 3 ghost zones in one message. And similarly, it's going to need a tiny little corner from that processing neighbor. And then it has everything it needs to compute with no more communication to get all the iterates at the top. And so you can imagine what the pattern looks like more generally. I won't try to do this in 3 dimensions. OK, but it's a very similar idea for optimizing sparse matrix vector multiply. It's just now there's more things that we can do because we don't have matrix entries to worry about. OK. So there's lots of papers to get more information about all this. For tuning stencils, there was a recent thesis by Kaushik Datta, and there's a whole bunch of technical reports. People are trying to put this into compilers so it can be done automatically. The hope is that you would just write the most natural, simple code with nested loops, and then the compiler would recognize, oh, I can do all these optimizations for you automatically. And there's someone with whom we have a joint grant named Michelle Strout, so there's certainly joint projects available to try to use that kind of compiler technology. And people have done this in other processors in the past. For example, a grid is a whole bunch of geographically distributed computers. You can imagine communications are really expensive there, and people have tried this technique there too. These ideas have been around for a while. Just to give you a sense of history, here's a paper that pointed out some of these ideas back in 1993, and in fact, they tried to apply it to multigrid, an algorithm we'll get to. And the very oldest paper we found back in the day when it was core memory and slow rotating disks, or maybe they were called drums, 1963. All right, but communication has been important for a long time, and so you can find hints of these ideas before. So hopefully we will stop reinventing and automate at this point. So anyway, and prove lower bounds too, so we can. That's another reason to stop reinventing. Okay, so that's what I wanted to say about Jacobi, and I'm going to keep using those techniques over and over again, but that's sort of the simplest one. And so let me go on to how to improve that. And so the next better algorithm was originally motivated by saying, OK, Jacobi converges very slowly. How do I improve that? And so one of the ways to do it is to say, well, once I've updated the points, I've gotten partway through a Jacobi iteration. Some points are updated, some aren't. Why don't I always use the most recent data? If I've already updated my neighbor in a previous iteration, let me use it, right? Because it's a better answer. So that's one optimization people wanted. And the other one is that if moving in this direction, if moving from iteration m to m plus 1, that's sort of an increment of some size. If that's a good direction to move, let me just go farther in that direction. Let me go twice as far in that direction, or some magic number. So there's going to be some magic constant to pick that people have done. Okay, so let's talk about how that's affected parallelization. And the algorithm that people invented for this is called Gauss-Seidel. So let me look at this loop first. So here is the inner loop of Jacobi. It says that at the m plus first iteration, I go get the the values of my neighbors, my left neighbor, my right neighbor, at the previous iteration. And so instead of always getting the mth iterate, I'm going to get the latest. Because if I've already updated my neighbor to my left, then I should use the latest information. So depending on the order in which I visit my neighbors, the latest could either be the previous iteration or it could be the current one. So let's see what happens if we do that in the standard way people have done it, which is iterate through your array in rows. So update the first row, update the second row, and so forth. Finally, let's suppose I get to here. So I'm ready to update this guy. Who is new and who is old? So I have 4 neighbors, there, 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 and there. These guys I've already updated. I did those in the previous iterations. These I have not updated yet. And so I would grab them at iteration m, and up here it's iteration m plus 1. Do you see that this is a completely sequential loop? If I want to parallelize this, there's nothing I can do, right? Because if I'm going to respect this dependency, then I have to compute them in this order, row-wise, in order to get the information. So when people saw that, they said, well, All right. Let me use the same trick. I'm always going to use the latest information, but let me not update it row-wise. Let me update it in a different order and still always use the most recent information. So the trick is motivated by chess. I'm going to update all the black nodes first, all of whom have red neighbors. And then I'll update all the red guys, all of whom have black neighbors. So here's the idea. So my first loop is going to be over all the black points, so every other mesh point. And if you look at all their neighbors, they're all of a different color, so all of them are going to be not updated yet. But I can update all the black ones in parallel. Then, once all the black ones are updated, I can go look at all the red ones. Their neighbors are always black. They're always updated, so I can now do all of those in parallel. So in 2 parallel steps, I can do all the blacks and then all the reds. And that is called red-black Gauss-Seidel. Now, this makes perfect sense if you have a 2-dimensional mesh. And you can sort of imagine what happens if you have a 3-dimensional mesh. But you could have a more complicated graph, right? So there's a technique from graph theory called graph coloring, of which red and black are a very special case. So, and we talked about this before, something called independent sets. So there's an algorithm which will take your graph and figure out what's the minimum number of colors to color it so that your neighbors are always a different color than you are. So this is a classical problem. How many colors does it take to color a map, right? The 4-color theorem, right? So if it's a planar graph, we know we can do it with 4, but there's much cheaper algorithms than that. And so the number of parallel steps you take will be the number of colors. For simple meshes like this, we know red, black, or if it's 3 dimensions, you need, red, black works too. Okay, so that's obviously a way to parallelize it. So let me now give you one more optimization that people have done on this. Again, this is all specialized just for Poisson. So I'm going to do red-black Gauss-Seidel. And if I do it, it turns out it converges twice as fast as Jacobi. So if you do the iteration, the error gets smaller twice as fast. But I take twice as many parallel steps, because I have to do the reds and the blacks separately at every point. So in practice, that optimization by itself doesn't help a whole lot. So we're going to add one more improvement. So here's the general formula. I have my value at the ijth mesh point at iteration m. I want to get the updated iteration m plus 1. And there's a formula. There's a correction, some value that depends on my nearest neighbors. So the motivation says that if this is a good correction, let me just go farther in the same direction. I'm just going to take that correction and multiply it by a magic number w that's bigger than 1 and hope that gets me to the answer faster. And it turns out that people have done a lot of theory in this area. And here is the magic number that's bigger than 1 that you should use for Poisson's equation. And it drops the number of steps to converge by a square root. So instead of taking, if you have a little n by little n mesh, instead of taking n squared steps to converge, you only take n. That's an asymptotically faster convergence. And I'm not going to do the theory for this. That's the topic of a math course. But this is the sort of optimizations people put in. And now the complexity has dropped from n to the 4th, little n to the 4th, to little n cubed, which is a worthy improvement. OK. And so that is SOR. One slide summary. I think I'm going to do multi-grid next time because it's a long topic. So just one slide on this last algorithm. And so this is, again, for solving AX equal B. And I mentioned this in the case of sparse matrices, the sparse dwarf before, but let me just repeat it for you. What's the inner loop look like? I'm going to do a matrix vector multiply, average with my neighbors. I'm going to do some dot products, some Saxbys, multiply a vector by a scalar, add it to another vector. And I keep on repeating that, updating an error called rho until it's small enough. And so, again, all the time is spent in doing a matrix vector multiply, and all those optimizations I told you about can be used to improve this as well. And so I just want to remind you that's part of the same design space. I don't want to go into the details here. So that is a good place to stop, because next time we'll talk about multigrid, which actually hits the lower bound and is the fastest algorithm and is very popular. OK. Are there any questions? So homework going out later today and due after spring break. And then I will put up a note on the web page encouraging you to come up with a short proposed class project and send that to me before spring break.